Alright, hello again. So this is a follow-up video to the previous AWR simulation software that we saw. And in this video, I would be describing an actual low-pass filter that we designed in the AWR and Axiem RF simulator that was shown in the previous video. So these are the specifications given in table 1.1 that we have to design the low-pass filter with. It would have a response type of equal ripple 0.5 decibels with a cutoff frequency of 2.4 gigahertz and the characteristic impedance of 50 gigahertz with insertion loss requirement to be greater than 30 dB at the design frequency of 4.8 gigahertz, which is double the cutoff frequency, having the electrical length of 45 degrees. And in the previous video, we saw we can choose the dielectric material that is given in the TX line tool as per table 1.2. That is basically the material constraint that we have for our low pass filter. Right. Well, first of all, we performed the simulation of this low pass filter in the AWR, and late in the later stage, we basically printed it PCB files, and then obtained the frequency response from the actual physical PCB. By frequency response, I mean by visualizing and analyzing its scattering parameters, namely S11 and S21, as is required. So these are the design specification. Based on these design specification, we perform the theoretical calculations with the given cutoff frequencies and the insertion loss. So since it's a response type is equal ripple, we use the following passband curves, and um, with the insertion loss of greater than 30 dB, we obtained the parameter n to be equals to 4. But in order to ensure matching, we have to select a the value of n which ensures matching. So instead of n equals to 4, as per this intersection right here, we can select to n equals 5 in order to ensure that the matching is taken care of. So with n equals to 5, we have the following parameters as shown here. For G1 all the way till G6, we can use these parameters to find the characteristic impedances of the inductive lines as well as the capacitive lines, as shown in the table right here. So also the design specifications is done using both the T network as well as the pi network. So I would share this manual with this video, and you can go through the details of the T network as well as the pi network. Right, so this is the table for the T network with the given inductive and capacitive line characteristic impedances. We obtain the corresponding microstrip width, length, and the electrical length as well, along with the lambda g and e effective as well for each of these parameters. Once we have this table specified, we can specify these particular characteristic of the microstrip within the design tool of AWR, and based on that we can obtain the schematics and the layout of our RF circuit. So this is what the T network is going to look like. We'll have three inductive elements and two capacitive elements, and the output characteristic impedance of 50 ohms, obviously. Similar to T network, we have this pi network right here, which is again with n equals to 5, and following are the parameters that are calculated for the microstrip using the inductive and capacitive line characteristic impedances. So for the simulation purposes and also for the printed circuit board, we use the pi network. Either of them would have given the similar results, but pi network was proven to be more geometrically feasible to implement on the PCBs instead of the T network. So we went along with the pi network for the PCB printing. And similarly, this would be the schematics of the pi network with three capacitive elements and two inductive elements for the impedances. Once we had that, as I showed you previously, we implemented the circuit in the pi network. We implemented both T network and pi network in the simulation environment, but only implemented pi network on the PCB. So here we are given the actual implementation of the schematics for the T network, and as you can see, we have the transmission line parameters given here with since n was equals to 5, so we have 5 of these elements with the closing ports having the characteristic impedance of 50 ohms, and each of these transmission line segments would have corresponding length and width according to the table that we saw above. So just select them, and you can also tune them according to the design specification that was also given in the table above. So this is for the T network, and similar to that we have for the pi network. But before that, we obtained the frequency response for the S11 and S21 scattering parameters. And as you can see, the cutoff frequency here is 1 point sorry 2.4 gigahertz right here, as per the design specification, with the gain of minus 32 dB, which is according to the insertion loss requirement. Similar to S11, we have S21, and you can see the cutoff frequency here is at 2.4 gigahertz, and with the gain of minus 3 dB, which is in corresponding to our design specification. Similar to all right. So before that, before the pi network, for the T network, we obtained the layout. So this was the layout, and as you can see, the middle line was quite thin, so it was really difficult to implement it on PCB, and that is why we went along with the pi network. So this was the schematic top view, as I showed you in the previous video as well. So this can be obtained using the layout, and this was the corresponding mesh view for the T network, and this is the 3D mesh view for the T network that can be printed. We obtain its corresponding Gerber files, and then we analyze whether it's feasible to print or not. Since the middle line was quite thin, and the PCB had its limitations, so we went along with the next pi network as discussed in this video. So similar to the previous one, we first performed the simulation with the following transmission line segments and the closing ports and the corresponding length and widths, and tuning them according to the design specification, then obtaining the S11 and S21 scattering parameters, and obtaining and analyzing their graphs in order to see whether it meets the design specification of cutoff frequency of 2.4 gigahertz with the required insertion loss gain, as well as the cutoff frequency within the S21 parameters with the gain of minus 3 dB. Right. So both of them, both T network and pi network, were feasible within the simulation environment, but as you can see here, for the pi network, we have the corresponding um, inductive lines to be much thicker compared to the T network, so it was much more feasible to be printed on the PCB. So we went along with the pi network, and you can clearly see that in the layout that it's more feasible to be printed with a physical board. So the corresponding 2D mesh view and 3D mesh view looked something like this. They can also be obtained within the AWR and Axiem simulation environment, um, as discussed previously. So once we have selected the pi network to print, we then performed its simulation, and then obtained its Gerber file for the layer 1 and layer 2. Layer 1 corresponding to the components that were the components of the transmission line, and layer 2 corresponds to the grounding layer, as you can see in the figure right here. So this background is the grounding layer, and this top yellowish layer corresponds to the components of the transmission line. And finally, once we had the printed circuit board, it looked something like this. So we used the key site and vector network analyzer in order to obtain the parameters S11 and S21. And this is the actual low pass filter that was printed on the PCB. And as you can see, it is similar to the one that is shown here in the layout of the pi network. So this was connected to this vector network analyzer right here of the key site, and using this vector network analyzer, we obtained the following results from the physical board. And as you can see, this is the key site's own GUI for the vector network analyzer to visualize S11 and S21 parameters. And corresponding to that, we have the following MATLAB plots, which conforms with the design specifications. And finally, we have discussed the final results in the summary. So this is it, and I will see you probably in the next video. And this is it for the design of the low pass filter using AWR Axiem and its corresponding PC. Thank you.